BGP is a notoriously overwhelming topic, mainly because it has so many moving parts to it. So in this video, we're going to take a closer look at BGP attributes and just how Fortigate performs the dark science of path selection. So I put together this topology and I hope that it has got enough depth and complexity so that we may illustrate all of the concepts. And speaking of this topology, in the middle, we have 3 internet service providers. This is an environment that we do not manage, that we don't have any control over. And their environments have already been configured. They're just waiting for us to bring up our part of the neighborships. So let's get straight to it, starting with firewall 3. So on firewall 3, we have 2 networks. We have the 35 network, which is the segment that is facing R5, and then the 34 network, the one facing firewall 4. And of course, we are .3, and our neighbors would be .5 and .4 respectively. Our autonomous system is 340. And our router ID will be 3.3.3.3. Our first neighbor would be R5, which would be 172.168.35.5. And the remote AS is 157. We'll enable software configuration and then move on to firewall 4 neighborship. That one is 34.4. And the remote AS is 340, which makes this an iBGP neighborship. And we'll also set software configuration enable. Now on firewall 3, the only network that we're going to advertise is 35. And that prefix is 172.168.35.0/24. That's the only network that we're going to advertise. Now let's verify our BGP config. We have our AS, we have our router ID, we have 2 neighbors, each in their own autonomous system, and we're advertising 1 network. Now let's see if our BGP has come up with R5. And as expected, that neighborship is up. We're sending and receiving. We're learning prefixes. It looks all good. Now onto firewall 4. Also on firewall 4, we have 2 networks. The network that is facing firewall 3 and the network that is facing router 2. Now we go on to our BGP. Our autonomous system is 340. And this router ID would be 4.4.4. I'll define 34.3, firewall 3 as our first neighbor. And the remote AS is 340, same as ours. I'll also enable software configuration. Our next neighbor is 172.16.24.2, which is R2. And their remote AS is 260. I'm also enabling software configuration. Now the last thing is to advertise our network, the segment that's connecting us to R2. And that prefix would be 172.16.24.0/24. Now, I expect when we check our neighborship that we would have a neighborship with firewall 3 and R2. As we can see that we are receiving prefixes already from R2, even though the neighborship has come up with firewall 3, we are sending and receiving messages. We are not yet exchanging any prefixes, but that just takes a minute. Let's now refresh and see. And yes, now we're learning prefixes from both. I believe we're done on autonomous system 340 with firewall 3 and 4. Now let's move on to autonomous system 900 on firewall 9. So on firewall 9, the same as firewall 3 and 4, we are working with these 2 networks, the segment 79 is connecting firewall 9 to R7. Segment 89 is connecting us to R8. And then we also have the loopback interface here, which is what we're going to advertise from firewall 9. So firewall 9 will therefore advertise 3 networks into BGP. Our autonomous system, our router ID would be 9.9.9. Our first neighbor, let's say R7, 172.16.79.7. Set software configuration enable. And the remote AS for R7 is 157. Our next neighbor would be 172.16.89.8. That's R8. And that remote AS is autonomous system number 800. We're also enabling software configuration. Now the last thing is to advertise the 3 networks. Our first network would be 9.9.9.9/32. And our second would be the link to R7. That's 79.0/24. And last but not least, 172.16.89.0/24. That's our link to R8. Now, if everything went okay, both neighborships with R7 and R8 should be up, and we should be learning prefixes. And indeed we are. Now let's have a look at our BGP table. There's a lot of routes, and we are learning multiple prefixes from multiple sources, which is expected because we're peers with 2 sources, so R7 and R8. Now let's have a look at the route table. The route table, we're only interested in the part of the route table that is populated by the BGP protocol. And to simplify things, I'm only going to be focusing on 2 prefixes, the default network as well as the network to 2.2.2.2. The very first thing that stands out for me is that all of these prefixes have R7 as the selected path, and we know that from the BGP table we are learning all these prefixes from both R7 and R8. Let's take a closer look at one of the prefixes and then see why that is. I'll take this first one, the default route, the default network. And like we said, we know that we are learning that network, the default network, from both sources, from R8 and R7. R7 has been selected as the best path. Let's figure out why. If we start with AS path, we can see that there's 2 hops in the AS path and 2 hops in the AS path for both R7 and R8. So that metric is the same. Both R8 and R7 are advertising this with the origin code of incomplete, and the metric is 0. The local preference is 100. Both routes are valid. Both routes are external, but the update from R7 came in at 11:24:51, whereas the update from R8 came in at 11:25. So BGP has selected R7 to be the preferred path, just simply based on age, the first come first serve principle. But this is not how we want to run our networks. We want to administratively configure which path our network traffic must follow. Let's assume for a moment that the link to R8 is a 1 gigabit link, whereas the link to R7 is a 500 meg link. So this traffic should in fact be going via R8. And when I'm in this traffic, I'm just speaking specifically for the internet traffic. the default network. And the way we're going to do that is work with our first attribute, wait. Historically, we've learned that wait is an attribute that is Cisco proprietary. It is not part of the RFC standard, but Fortinet have their own implementation of BGP that includes wait. That's why we're able to configure wait, and that's exactly what we're going to do in this lab. So it's locally significant on the router. Where you configure wait on this router, for instance, we're going to be configuring it here on firewall 9. That attribute will stay there on firewall 9. It will not be advertised or propagate to any other neighbor. For that reason, it's non-transitive. And the last thing about wait is the default values. Wait has two default values, the value of 0 and 32768. Let's have a look at our BGP table. Looking at our BGP table, we can see as far as wait is concerned, everything is the same. Everything is all zeros except for 3. The 3 values have one thing in common. The first one is the 9.9.9. We know this to be the network that we originated, the network that we advertised, as well as the 2 links, one connecting to R7, the other one connecting to R8. This tells us that the networks that we originate, the networks that we advertise, they would have a default value of 32768. All the networks that we learn that have been advertised to us would have a default value of 0. And the higher the value, the more preferred the value is. In our example with the default network, where right now R7 is the preferred path, but we want this traffic to go over R8. If we're going to work with wait, anything higher than 0 would be preferred. So we're going to configure R8 to have the weight of, say, 1. And the way we're going to do that is we're going to create a prefix list that matches this network, just the way it appears like this, and apply that in a route map with the neighborship to R8 and modify our weight so that the path via R8 would be preferred. So first, let's define our prefix list to match this exact prefix. I'm just going to call this default network because that's exactly what it is. And our first entry there would be that prefix as it appears in the route table. Now, we want to modify the prefix for the default network, but we don't want to influence everything else. This means that we need to create something else, another prefix list that's going to match. Firstly, we are matching the default network, but then we need to have a prefix that's going to match everything else, because we want to be able to contrast between what we want to modify, what we want to manipulate, and what we want to have left alone. So we need to create a prefix list. In this case, I'll create one called other networks, for instance. And that prefix is going to match any. Now let's have a look at our prefix lists. So we have our 2 prefix lists. The first is what we're interested in, what we're going to manipulate with our route map. And the other one is essentially saying match other networks, because if we want to use the route map, a route map will match the traffic that you specify, and the default action is to drop everything else. So that means if we match this first entry, the default network, other networks may be dropped. We don't want that. So, and that's why we need the other entry. Now onto our route map. And I'm also going to call this default network. And our first entry would match the default network prefix list that we created. The IP address, default network. Now that we've matched that, what we want to do, we want to set weight to, let's say 1. 1 is higher than 0, so this will work. So we've matched our traffic that we're interested in, but for everything else that we want left alone, let's create a second rule. Match IP address. That's the one that we call other networks. And here we don't do any modifications. We just exit out of this. Let's review our route map. The first entry does what we want, and the second entry leaves everything just as is. This is good enough for me. Now we need to go onto our BGP config and apply this route map with R8, so that this config here will apply to the advertisements as they're coming in from R8. And the command there is set route map in. It's a route map in because from the viewpoint of firewall 9, the advertisement for the default network is being advertised to us by actually both R8 and R7. So it's coming in the inbound direction. That's why we have to use route map in. And now we specify the default network route map that we created, and we're done. And now the last thing I want to do is just force the BGP update by just resetting everything. Now let's check on our prefix again. Get router info, BGP network 0.0.0.0. Now we can see that the best path is through R8. And if we have a look at the route table, we can see that the default network is now going over R8. Now for the next attribute, local preference, we actually have to go to firewall 3 and 4 in autonomous system 340. Now on firewall 3, let's have a look first at our BGP table. Get router info, BGP network. And as we can see here, we have multiple paths to multiple prefixes, multiple network destinations. Now let's have a look at our route table. And the thing that stands out here as well is that out of all these prefixes, they seem to be learned or preferring the path via R5. And that looks a little bit strange to me. So let's have a look. Let's maybe consider one prefix. Let's look at the default route again. So I'll copy this so we can take a closer look at this prefix. Get router info, BGP network, that one. So looking at this, we know we are learning it from both R4 and R5. But what's interesting with R4, or rather firewall 4, we can see that it says it's inaccessible from firewall 4. Let's have a look at another prefix. Let's say maybe this one. This prefix is being advertised by firewall 4, but it's also inaccessible. And the specific problem here is that firewall 3 cannot forward the traffic out to R2 because it's not directly connected. It cannot be the next hop because it's a hop after another hop. So to fix this, this is why the next hop self is an important configuration parameter in iBGP. So we need to configure that on both firewall 3 and firewall 4 to fix the situation. So while we're in firewall 3, let's fix that here first. Set next hop self enable. And then onto firewall 4, we do the same. The neighborship of firewall 3. And let's go back to firewall 3 and display the BGP table again. I'm going to force a BGP refresh. And this looks much better. We have the next hop is firewall 4 and R5 for all the network prefixes. And now onto firewall 4. The same with firewall 4. This looks better. So from firewall 4, we can see that the default network is being learned via R2. But let's have a look at this prefix closer. Get router info, BGP network. And we're not receiving this prefix from anywhere else other than from R2. Instead, we are advertising this to our next hop, our neighbor, firewall 3. And I want to check on firewall 3 to see where we're learning this network from, the sources. 0.0.0. So firewall 3 is learning this route from both firewall 4 and R5. So since firewall 4 is learning this route only from R2 and advertising it to firewall 3, and firewall 3 has this entry coming in both from firewall 4 and R5, we're going to use local preference to influence the direction where this traffic is going to be forwarded, because currently to get to the internet, firewall 3 will pass the traffic down to firewall 4, which will then pass it to R2, the eBGP neighbor. We want to spin it the other way around so that the traffic is going to go out via R5. And for us to do that, we are going to work with the local preference. So unlike wait, the local preference is actually a well-known attribute. The thing about local preference though is that it operates only within the same autonomous system, meaning in our lab, local preference can only be configured between the routers in ASN 340 and also, for argument's sake here in 157, local preference can only operate here, but that attribute does not propagate out to the neighboring autonomous systems. So it is locally significant within an autonomous system. So on firewall 3, let's create our prefix list and our route map, apply it in the inbound direction coming in from R5, because we want to modify that prefix as we receive it from R5. Config router, prefix list. This is exactly the same thing that we did on firewall 9, and we're basically going to follow the same process. Our prefix list, I'm going to call it default. Our rule is going to specify the prefix 0.0.0.0/0. And again, we want to create another prefix that's going to match everything else so that we have something to contrast, and I'll call this others. The prefix there would be any. Just reviewing our prefix lists. This looks okay to me. Now let's create our route map. I'll call this default. We want to match the IP address called default. And once we've matched it, we want to set the local preference to 101. Now that's for the default prefix list. And now onto the other prefix list that is going to leave other networks untouched. Gonna review our route map. The first rule matches and modifies the local preference, and the other one matches and does nothing. Now onto our BGP. Now we're going to edit our neighborship with R5, because R5 is the direction where the prefix is coming in from, and we want to match the prefix, modify its attributes as it comes in before it gets into our rep table. And we apply the route map in. The route map is called default, and I'm going to refresh our peering with R5. Exec router clear BGP IP 172.16.35.5. And now the default network prefix coming in from R5 has a local pref of 100, and the one coming in from our neighbor R4 only has 100. So let's have a look now at firewall 4. Now back on firewall 4, looking at the same prefix, we can see now that the update has taken effect, and now firewall 4 prefers to get to the internet via firewall 3. And the reason for that is local preference. So local preference takes precedence or gets evaluated first before AS path. AS path is further down the line. So if you look at this, in fact, you'll see that we have 2 hops in the AS path field here, whereas this path has only 1 hop. So naturally, you would expect that the path would be 260, which was actually the actual initial behavior, but we just manipulated that a little bit, did a little bit of witchcraft to force this traffic over firewall 3. So the next attribute, originated, essentially says 2 things. If a network is locally originated, it's going to have a higher priority, and therefore it's going to be preferred. We saw earlier when we were looking at firewall 9, all the networks that were locally advertised, they have a weight of 32768, and everything else that was learned has a value in weight of 0. So if it's locally originated, it's going to have a higher value than a network that was otherwise learned, in which case it's going to have an indicator of I. But if it's a prefix that was redistributed into BGP, then it's going to have a question mark on it. Which then brings us to our next topic, the AS path. AS path is a well-known attribute. It's part of the RFC standard. That means it's mandatory. And because it's mandatory, it's also transitive. It's an attribute that is transferred between external autonomous systems or between eBGP neighbors. And since BGP is a path vector protocol, the fewer the autonomous systems in the AS path field, the better. Let's have a look at firewall 9. And on firewall 9, let's have a look at our BGP table. So we've already worked with the default network. I will not touch this again. So let's work on the prefix 2.2.2, because as we can see, this network 2.2.2 has exactly the same attributes coming in from R7 and R8, and the firewall 9 has chosen a path via R8. Let's have a look at why. Looking at this, the AS path is the same. There's 2 hops in the AS field, and the origin is, in both cases, IGP. The metric is 0, local preference is 100, and the only reason firewall 9 chose the path via R8 is because it is the oldest route, so it chose this on the basis of age, and we want to modify this. Age comes way down below AS path. Now we want to modify AS path to influence which way firewall 9 would follow to get to this destination 2.2.2.2. And so currently, because the best path is via R8, we want to modify the path via R7 to be the preferred path. So that means for us to do that, we need to make the AS path from R8 to look worse, to be longer in the AS path field. So That means we need to modify the advertisement as it's coming from R8. So on R8, the first thing is to match the destination network 2.2.2. That's access list 10, permit 2.2.2. Now we create our route map, network 2. And we want to now match our access list, match IP address 10, set AS path. We want to prepend the last AS just one time. And this is for our first statement. With the default action of implicit deny, we want to permit everything else. Route map network 2, permit 1000. And we take no action, we leave everything as is. And now we're going to use this route map in the outbound direction to firewall 9. Neighbor 172.16.89.9. So the command will be route map network 2 in the outbound direction. And on firewall 9, let's force a refresh of the BGP advertisements we're receiving from R8. Now looking at this output, now we notice that the path via R8 now has a longer autonomous system path, with the last AS 260 being prepended one time. Now we have 3 autonomous systems in the AS path field compared to 2 autonomous systems in the AS path via R7, making R7 a better path. And now a cleaner view of this in the route table. We see that for network 2.2.2, we prefer the path via R7 because it's shorter. The next attribute is going to be the origin code. And we kind of spoke about this already when we spoke about the originated attribute. The origin code is part of the RFC standard. That means it's well known, it's mandatory, and therefore it's transitive. With the origin code, the prefixes that come in, indicated by the letter I, essentially state that that network has been advertised into BGP by a network statement, therefore advertised by the routing protocol such as BGP. And those are preferred over networks that were redistributed into BGP. And to demonstrate that, I will hop on to R2, even though I know we said that we're not going to be touching the routers. It's just easier to demonstrate it from here. So let's review the config on R2. So run section router BGP. And on R2, we can see that the network 2 was advertised using the network statement, but we can actually also redistribute this into BGP. First, let's have a look at our BGP table. We can see that this network has an origin code of I because it was advertised by a network statement. Let's remove this from the BGP config and instead redistribute it. And now we'll redistribute that. Say redistribute connected. It'll be included in there. Show IP BGP. Now look at the origin code assigned or attached to the network prefix 2.2.2. So what happens if we leave the config the way it is? We have it redistributed. Let's add this again via the network statement. Now let's have a look at the origin code that's going to be associated with the prefix. We see that it has immediately changed, but R2 has inserted this as an IGP into the rep table. And because it has these two indicators here that it's best and valid, this is what's going to get injected into the route table and advertised out to other BGP neighbors. So the key takeaway here is that the networks that have been advertised by a routing protocol such as BGP would have origin code of IGP indicated by the letter I, and those are preferred over networks that have been redistributed into BGP. The next attribute that we want to be aware of is the MED, the multi-exit discriminator. It is a well-known attribute, but it is completely optional. The other thing about MED is that it is non-transitive. It is actually only relevant between the adjacent autonomous systems. In our topology, we don't actually have a kind of setup that allows us to configure and have a look at MED. If, say for instance, if R1 was part of autonomous system 260, it means R1 would have two legs or two paths to get to autonomous system 157. And what MED is would be R5 advertising a metric to R1, let's say 100. And R7 would also advertise its own metric. What the metric lower is better. So if R5 was to advertise a lower metric to R1, R1 would prefer R5. MED is only relevant where you have a device that has dual connections into the same autonomous system, which is an implementation we simply don't have in our environment. So for that reason, we'll skip MED. But the key takeaway there is if R1 was part of ASN 260, the metric would be propagating between ASN 157 and ASN 260. But ASN 260 would not advertise that metric to ASN 340 or ASN 800. That would only end between 157 and 260. It'll be limited there. And the word they use for that is it is optionally transitive. So now after MED, the next attribute that I want us to look at is eBGP over iBGP. And here the rule is the router or the firewall would actually prefer an eBGP path over iBGP. So we would prefer a path via an external BGP peer instead of a path via an iBGP peer. So it's eBGP favored over iBGP. And you'd recall that the networks that are advertised by eBGP peers have an administrative distance of 20, whereas the routes that have been advertised by an iBGP peer have an administrative distance of 200. So lower is better. And to demonstrate this, let's go back to firewall 3. Let's have a look at the destination to network 9.9.9. Firewall 3 is preferring the path via R5. Firewall 4 is preferring a path via firewall 3. And the reason this path is the best path is because it has a shorter path in the AS field. So what would happen if this path was the same? The AS path was the same, 3 hops in the AS field for firewall 3 and R2. Let's do that and have a look. We're going to prepend one AS to this AS path, and we need to do that from R5. That's access list 10, permit 9.9.9.9. And we create our route map. We call it network 9, permit 10, and we want to match IP address 10. And once we've matched this, we want to modify the AS path, and we want to prepend last by just 1, and the catch-all statement that matches all the other traffic and leaves that intact. Let's say permit 1000. Now we have our route map. We're going to apply that in the outbound direction to firewall 3. Our process is 157. Neighbor 172.16.35.3. Route map network 9 in the outbound direction. And on firewall 3, let's refresh our peering with R5. We're interested in 9.9.9.9. And as we can see, the autonomous system has been prepended. AS 900 has been prepended at least one more time. And now comparing the AS path from R5 and R4, we have 3 autonomous systems in the AS path, which means these are the same. So firewall 4 is receiving the new update with the new AS path, and now the best path has actually been updated. We see that the best path was initially firewall 3, and now the best path is R2. If we compare this attribute coming from both peers, we can see that everything from the origin, the AS path, everything is the same. The only difference here is now this source is internal and this is external. Therefore, the external neighbor and the external path is preferred over the internal path. And if we look at the route table, this prefix has an administrative distance of 20. The next attribute we're going to have a look at is age. We have actually been looking at this throughout the lab, but in this particular case, I want us to have a look at firewall 9 again. So back on firewall 9, let's display our BGP table. Get router info. So I'm going to be looking at this prefix over here, network 2. And although we did modify this, I want to take off the config that we put on R8 to prepend this AS. Let's start there with R8. And on firewall 9, I'm going to refresh the BGP process with R8. Now let's have a look at our BGP table again. Get router info. So now our prefix network 2.2.2 has 2 entries with the same values, the same attributes advertised both by R7 and R8. Let's take a closer look at the prefix itself. Network 2.2.2. So looking at this output, we can see that the update coming from R7 came in at 1338, where the update from R8 came in at 1421. So the oldest update coming from R7 is the one that's preferred. The next attribute that the firewall 9 would be looking at as a tiebreaker would be the router ID. So assuming the time was the same, the last update was the same from R7 and R8, the router with the lowest router ID, R7, would win. Where router IDs are also the same, which is rare or unheard of, then the neighbor's IP address would be a tiebreaker. And in that case, what the firewall will be looking for is the neighbor with the lowest IP address as well. This has brought us to the end of this lab. Thanks for watching and catch you in the next one.